Welcome. We're diving into chapters 14 and 15 today, which focus on acid-base chemistry. This is one of the most important topics in chemistry because acids and bases are everywhere, from the food we eat to the products we use daily. Over the next two chapters, we'll learn what makes a substance acidic or basic, how to measure acidity using the pH scale, and how acids and bases react with each other. By the end, you'll understand the chemistry happening in your stomach, in your swimming pool, and in countless industrial processes. Let's get started. This is a catalyst slide, a chance to activate your prior knowledge before we dive deep. I want you to think about what you already know about acids and bases from your own experiences. Maybe you've tasted something sour like lemon juice, or you know that soap is slippery. That's a base. These aren't trick questions. I'm genuinely curious what comes to mind. Take a moment to think about examples from your everyday life: cleaning products, food, your body. This foundation helps us build on what you already understand rather than starting from scratch. Who wants to share? All right, here's where we're heading in this section. By the end, you'll be able to distinguish between strong and weak acids and bases, not just by memorizing definitions, but by understanding how their properties actually differ. We're also connecting everything back to the Arrhenius definition, which explains acids and bases at the molecular level. Then we'll build your toolkit by learning the common acids and bases you'll encounter in chemistry, their formulas and proper names. Think of this as your roadmap for the next few lessons. Okay, here's your roadmap for mastery in this section. You've got 3 concrete goals to hit. First, you need to identify and articulate 2 key properties that characterize acids, and 2 for bases. These are observable behaviors and chemical traits. Second, you'll apply the Arrhenius definition to real examples, showing me that you understand not just what these substances are, but why they fit the definition. Finally, you're building essential reference knowledge, memorizing the 6 strong acids and at least 1 weak base. This isn't busy work. These are the chemicals you'll see constantly in labs and problems. Master these criteria, and you'll have a solid foundation for everything that follows. We're now diving into section 14.1, where we'll explore the observable and chemical properties that make acids and bases distinctly different. This is the foundational knowledge you need before we get into definitions and reactions. We'll examine what you can actually observe, taste, texture, how they behave with indicators, and then connect those observations to what's happening at the molecular level. Understanding these properties helps you predict how acids and bases will interact with other substances. Let's start building that framework. Now we're zooming in on what actually defines acids. These aren't just abstract definitions, they're real, observable characteristics you can test and measure. Notice the pattern. Acids have that sharp, sour taste. They change color with indicators like litmus paper turning red, and they break apart into ions when dissolved. The key chemical behaviors are that they react with metals to release hydrogen gas, which is actually a useful way to identify them, and they neutralize bases by combining to form salts and water. We also see they have low pH values. Each of these properties connects back to the presence of hydrogen ions. Now let's talk about how we actually name acids. There's a system here. Binary acids are the simpler category. They've got just hydrogen plus 1 electronegative element, and we name them by saying hydro, then the element's root, then IC acid. Think hydrochloric acid. Oxyacids are trickier because they contain hydrogen, oxygen, and usually a nonmetal. The naming pattern depends on the polyatomic ion suffix. If the ion ends in ate, the acid ends in IC. If it ends in ite, the acid ends in aus. This is why nitric acid comes from the nitrate ion. That's the naming pattern in action. Now we're shifting gears to bases, the opposite of acids. Bases have some pretty distinctive physical properties. They're slippery when you touch them and taste bitter. Chemically, they change the color of indicator dyes like litmus paper, turning it blue. Here's the key behavior. Bases are electrolytes, meaning they break apart into ions when dissolved in water. Like acids, they can be strong or weak depending on how completely they ionize. Most importantly, bases react with acids in a process called neutralization, producing a salt and water as products. This is the fundamental acid-base chemistry you'll use constantly. Now we're diving into the Arrhenius definition, which is the classical way to categorize acids and bases. According to Arrhenius, an acid is specifically any substance that produces hydrogen ions, written as H-pies or H3O-mi, when it dissolves in water. A base, conversely, is any substance that produces hydroxide ions, OH-ments, in aqueous solution. The diagram shows this in action. Nitric acid donates a proton to water, creating the hydronium ion and the nitrate ion. I want to highlight that this definition is limited. It only works in aqueous solutions and doesn't explain all acid-base behavior, which is why we'll see other definitions next. Now let's talk about acid strength. This is how we measure how readily an acid actually donates those hydrogen ions we discussed. A strong acid like hydrochloric acid breaks apart almost entirely in water, meaning nearly all the molecules split into ions. That's why they're also strong electrolytes. Weak acids, like acetic acid and vinegar, are the opposite. Most molecules stay intact, only a few break apart and release hydrogen ions. This distinction matters enormously in chemistry because it affects pH, conductivity, and how these acids behave in reactions. Here's your memorization list for the 6 strong acids you absolutely need to know. These are the only common acids that completely dissociate in water. Notice the pattern. Most are binary acids with hydrogen plus a halogen, plus the 2 most important oxyacids, nitric and sulfuric. This is your reference list. Write it down now. The key takeaway at the bottom is crucial. If an acid isn't on this list, assume it's weak. That one rule will save you so much time on exams and problem sets. Now we're shifting focus to concentration. How much acid is actually dissolved in your solution? A concentrated acid has a high molarity, meaning lots of acid molecules packed into that volume. Think of 6-MHCl as very strong and aggressive chemically. A dilute acid has a low molarity, like 0.10 mHCl, which is the same acid but much weaker in strength because fewer molecules are present. Don't confuse this with strong versus weak acids. Both concentrated and dilute solutions can contain the same strong acid. It's about the amount dissolved, not the acid's ability to dissociate. Here's where you apply what we just learned. You need to classify each acid on 2 independent scales. First, look at molarity to decide if it's dilute or concentrated. Remember, 0.001 mem is very dilute, while 1.0 mem is concentrated. Second, you need to know whether HI and HF are inherently strong or weak acids. HI is a strong acid. It completely ionizes regardless of concentration. HF, however, is a weak acid. It only partially ionizes. So be careful. A weak acid can still be concentrated, and a strong acid can be dilute. Take a moment and classify all 4. Now we're shifting from acids to bases, and the same principle applies. A strong base completely dissociates in water. Think of it like NaOH or KOH, which break apart into ions entirely. These are strong electrolytes. On the flip side, weak bases like ammonia only produce a small number of hydroxide ions. Ammonia is tricky because it doesn't directly donate OH-ments. Instead, it accepts protons and causes some water molecules to release OH ions. The key distinction: strong bases go all in, weak bases hold back. Memorize NH3 as your classic weak base example. Today, we're setting up our learning goals for acids and bases. By the end of this section, you need to understand what makes an acid or base strong versus weak, and you'll connect that back to how Arrhenius originally defined them. You'll also memorize some of the most common acids and bases you'll encounter in chemistry. Knowing their formulas and names is essential because they come up constantly. Think of this as building your foundation. Once you know the definitions and can recognize the key players, everything else about acid-base chemistry will make sense. Here's what success looks like for this unit. You need to master 3 concrete goals. First, you'll identify and articulate 2 key properties that distinguish acids from bases. Think about their taste, reactivity, and how they feel. Second, you'll take specific examples like hydrochloric acid and sodium hydroxide and explain them using Arrhenius's definition. Acids produce H plus ions in water. Bases produce OH ions. Finally, you're going to memorize the 6 strong acids: HCl, HBr, HI, HNO3, H2S4, and HClS4, and at least one common weak base like ammonia. These aren't arbitrary facts. They're the building blocks you'll use constantly in reactions and calculations ahead.